Math 2415, section 10.5, equations of lines and planes, parametrizing a line segment. In the previous two videos for this section, we came up with different ways to write the equation of a line in space. We wrote it in vector form, or as a vector equation. We wrote it as parametric equations, and we also wrote it as symmetric equations. And we worked an example that contained several steps. But sometimes you want to be able to come up with equations that will give you not an entire line, but just a line segment. When we get to chapter 13 and study line integrals, we will need to be able to come up with parametric equations that don't give us an entire line, but just a portion of it connecting two points. For example, let's find the vector equation in parametric equations for the line segment connecting vector R0, vector 7, 11, 10, and vector R1, whose component form is -2, 5, -1. Keep in mind that when we talk about a line connecting two vectors, we're really thinking about these vectors as having initial points at the origin and connecting their terminal points. In other words, we're thinking of these as ordered triples, not necessarily vectors. Well, how can we do this? Well, we already have a plan of attack for finding the parametric and vector equations of a line connecting two points. Recall that we can come up with the equation of a line if we know a point it goes through and a vector that's parallel to it. Specifically, it was r is equal to tv plus r0, where r0 is a specific point, and v is a parallel vector. Well, we're not given a parallel vector, and again, it might help to draw a picture of this. You can draw your frame of reference however you want, but I'm not going to draw a standard x, y, and z axis. I'm just going to put the 2 points up here, r0 and r1. r0 being the vector 7, 11, 10, or rather I should say the points 7, 11, 10, and r1 being the vector -2, 5, -1, and again I should say the point -2, 5, -1. Somewhere there's an origin. I just didn't draw the x and the y axes. So let's put the origin here, so that when I say r0 as a vector, I really mean this vector from the origin. And when I say r1, I mean this vector from the origin. And if we want to find the equation of the line, which would not end at either of these points, then we just need we need a parallel vector, and recall that we can find the parallel vector by simply subtracting these two vectors. For example, if I took the vector from the terminal point of r0 to the terminal point of r1, then that vector would be r1 minus r0. And if you ever forget which order the subtraction problem goes in, just look for the vector addition problem. r0 plus something has to equal r1. The thing I can add to r0 to turn it into r1 is the subtraction problem. Oh, wait a minute, we can calculate this vector because we know both r1 and r0's components, so we can just subtract r1's components minus r0's components. -2 minus 7 is -9, 5 minus 11 is -6, -1 minus 10 is -11. All right, maybe I should have subtracted them in the other order, but that's okay. We'll go with the one who's completely negative in all three components. So what does this mean? This means that we can write this equation as r is equal to t times this, because that's our parallel vector to the line, -9. You know what? Let's do this generically first. I'll write this component form of the parallel vector in a moment, but recall that we're really just looking for something that tells us the direction of the line, the parallel vector, if you will. So instead of writing -9, -6, -11, let's keep it generic for a second and say that we calculated this parallel vector by taking one of the points, which we call R1, and subtracting the other. Okay? And again, we could put in all the numbers. We could put in the numbers for R0 and R1, subtracting at this, and do the things we did before. But keep in mind that we're trying to come up with the equation of just this line segment, not the entire line. When we have the vector equation, we get the entire line by letting the parameter t assume any real number value. Just keep in mind that t is how many copies of this parallel vector you have. So for example, if I start here and want to go twice as far, t would be 2. Or if I wanted to go backwards 3, t would be -3. In order to get the line segment though, I can't let t assume all real numbers, otherwise I would get the entire line. What values of t should I assume? Well, keeping in mind that t counts how many of the parallel vector you travel from your initial point, which we're calling R0, how many of these arrows do I need to get from here, the green point, to here? It's kind of a simple question. The number of these blue arrows I need to get from the green point to the red point is one of them. So if t equals 1, it takes me here. If t is greater than 1, then it goes beyond that. So one thing we know about our parameter, in order to keep the line segment and nothing else, is that t has to be less than or equal to 1. Otherwise, it shoots me too far past the red dot. But I also have to make sure that it doesn't go backwards. Well, if the t is going to send me backwards in the direction of the parallel vector, then the t would have to be negative. So the t can't be negative. But what happens when t is 0? Well, t counts how many of the blue vectors you travel starting from this point. And if t is 0, you travel none of them and you stop where you start. In other words, this point here that we decided to call R0 would be where we would be when time equals 0, if you will, when we haven't traveled any of the parallel vectors. And when we travel it once, it takes us over here. So t can assume any value that's greater than 0, but simultaneously less than 1, because that just means we'll start here. We'll go a little ways, but we won't go further than one of those vectors, which takes us from the first point to the second point, which means we can restrict t to being between 0 and 1. That's how you parametrize a line segment that has a finite beginning and a finite end. You say the parameter is going to go from 0 to 1. You put the point that you start here, and you put the direction vector found by doing I want to say second minus first, so let me use naught and 1. Put R0 here, and then the direction vector is R1 minus R0. So that gives us the parametrization of this line segment. Now, we can write this a little bit differently if we gather like terms. We can do that by distributing the scalar t across the subtraction problem. Then we can gather the R0s and factor them out. So I'm going to do a couple of algebra moves, or more than a couple. I'm going to take both of these R0s and put them in front, but I'm going to switch their order to say R0 minus t times R0, at which point I can factor out the R0, and that would leave 1 minus t, plus, and then I'm going to write t times R1 second. Keeping in mind that our parameter is between 0 and 1, this, which actually is a function of t, so I could go back here and say, hey, calculate the vector based on the value of t. This is the parametrization of a line segment that starts at R0, ends at R1, and assumes every point in between. So for this particular example, I guess we owe it to do it, our parametric equations, or equation in vector form, would be 1 minus t times R0, which was 7, 11, and 10, plus, well, that's right, never mind, plus t times R1, which was -2, 5, -1. And that would be a perfectly, and t is limited to 0 and 1. or in the interval 0 to 1. And that would be a perfectly good parametrization of this line segment. Now, if you wanted to, you could distribute the scalars and combine components. And we can do that in one move if you're careful. For example, let's examine the first component. I'm going to get a negative 7t here and a negative 2t there, so I would get negative 9t. But I would also get 1 times 7. I wouldn't pick up a constant over there. 1 times 7 is 7, so negative 9t plus 7. In the second component, for the t's, I would get negative t times 11 is negative 11t. And then plus 5t, negative 11 plus 5 is negative 6t. Oh, not done. And the constants, which come from 1 times 11, which is 11. And then in the third component, if I gather up the t's, negative t times 10 is negative t times negative 1. Let me try that again. Negative t times 10 is negative 10t. T times negative 1 is negative 1t. Negative 10t and negative 1t is negative 11t. And then for the constant, we would have 1 times 10. And again, there's no constant we pick up over there, so plus 10. And this really shouldn't surprise you, because we had already calculated the component form of the parallel vector, negative 9, negative 6, negative 11. And if you notice, those are the coefficients of the parameter t. And the point that we started at, 7, 11, and 10, is what looks like a y-intercept. And again, without this restriction on the t, that gives us the entire line. In order to guarantee only the line segment, we would have to limit the t to being between 0 and 1. All right, so let's kind of summarize what just happened here, because we were doing an example and at the same time developing an idea. For those just saying, tell me what I need to know, here's what you need to know. Oh, I'm sorry, we never wrote the parametric equations for this. Okay, x equals this, y equals this, z equals this, still with the restrictions on the t. The vector equation of the line segment connecting R0 to R1, and I'm kind of implying that it's connecting it in that order. We're not really talking about orientation of curves right now, but later when we do, the direction in which the curve travels, in this case by curve I mean a line, the direction in which the line travels is called its orientation, and later on it does matter which way we orient a curve. But back to this, the vector equation of the line segment connecting R0 to R1 is R of t equals 1 minus t times R0 plus t times R1, with the restriction that t is greater than or equal to 0 but less than or equal to 1. It's actually not that hard to memorize this. You just have to remember a couple of things. Number one, the scalars are either t or 1 minus t. T or 1 minus t. Number two, which one goes in front of which? Well, remember, at time equals 0, we start at R0. So putting in 0 has to get rid of the R1 and leave the R0. Putting in 0 does get rid of the R1. 1 minus 0 is 1. We get 1 R0. So we start there. And we have to end at R1. So putting in t equals 1 has to leave us R1 and get rid of the R0. So putting in t equals 1 here gives the R0 a coefficient of 0. It's gone. Putting a 1 here gives a coefficient of 1 in front of the R1. So in other words, when we start at time equals 0, we are at R0, and when we end at time equals 1, we're at R1. So it's not a coincidence that that happens. It was designed that way because we started at one and ended at the other.